of the fundamental theorem of calculus in both of its glorious parts. So let's sort of recap what we've learned so far. Okay, so FTOC. There are really kind of two big pieces to it, and we're going to just sort of continue with the exploration of both pieces. And also there's a wrinkle with, well, both of them. And we'll sort of talk about the wrinkle a little bit today. So the first, okay. Don't necessarily think that these have to come in either order. So I have seen, like pretty much every calculus book out there talks about the two parts of the fundamental theorem, but they don't agree on what the two parts are, right? So somebody's part one is the other book's part two and vice versa. Okay, so just, there are two parts, just, right, okay. So the first one says, how can you do an indefinite integral, or excuse me, a definite integral, if you know an antiderivative of the function? Okay, so remember, what's the definition of an antiderivative? Big F is an antiderivative of little f, means that the derivative of big F is little f. Okay, good? All right, so provided that you have an antiderivative, then a definite integral is really just a matter of plugging things into this antiderivative and subtracting and not botching the arithmetic. Okay? The wrinkle and the hard part is actually finding the antiderivative. If you know it, you're done, right, basically. It's just plug in some numbers, subtract, off, finished. The hard part is finding the antiderivative in the first place, okay? And in fact, sometimes that's actually impossible, like literally. So not just impossible, meaning really, really hard, like outright impossible, okay? Sometimes it's really, really hard, but still possible, right? So yes. And seeing you two and me just reminded me. So if you were currently in the class or online, Nolan, you two are safe. I'm safe. Why am I safe, and why are they two safe? Huh? What? No. COVID app. That's not the green I'm referring to. Right. It's St. Patrick's Day. Do you have an item that's green on your body?
I don't really know.
You don't? What do you mean you don't really know? Are you colorblind?
Not really, no.
Oh, okay. I thought you said, I don't really know. And I'm like, All right, rest of you? All right, if you don't have green on, commence pinching yourself. Sorry.
I do not observe St. Patrick's Day.
Huh?
I don't observe St. Patrick's Day.
Oh, it's...
Actually, I forgot.
Okay, all right, well, we'll give it to you this time. But next year, you better come into class in a full leprechaun outfit, or else you fail. Right, so, all right. And believe me, if you weren't all freshmen, nothing would be more fun than just you come into class and, surprise, we're going to have bangers and mash and drink Guinness all morning. So that'd be kind of fun, right? Yeah, anyway. All right, so the hard part is finding the antiderivative. Once you've got it, it's pretty easy, but getting that is tough. Okay, the other part of it is if you have a function that's defined as an as a sort of quasi-definite integral. Okay, so first off, let's just make sure we're clear. This integral from a to x of f of t dt, that really is a function of x. Okay, even though there's t's in it. Okay, is that all right? Yeah? All right, and so if that's a function of x, I could ask, well, what's the derivative of it with respect to x? Reasonable question. And we did a few of those last time where I picked really, really simple functions for f of t, you know, like straight line, a horizontal line, and then we did a straight line that had like a easy slope. And we kind of figured out what was going on. But what we ended up with, right, was a function of x, and then we took the derivative of it, and we got whatever we got. Okay. So what does the fundamental theorem say that this is? Well, okay. This, the integral part, is an area, right? So what we're asking was, what's the derivative of that? Okay. And this is the thing that when you see it, it's like almost too good to be true. It's just f of x. No, f of x, because x is the variable, right? Okay. So actually, that does bring up a good point, which the t and the dt here are what we call a dummy variable, insofar as, could I have written f of smiley face d smiley face? And it would have still been exactly f of x when the answer's finished with, right? So in that sense, we call t a dummy variable because it doesn't really matter what letter you pick. With one exception, what's the one letter we shouldn't pick? X, because we're already using it in a different way. Okay, and yeah. Okay, so that idea, I can't think of any other instance that you guys would have run into this idea of a dummy variable, except maybe in like computer programming. How many of you guys have done any computer programming? I mean, 2 of you I know for certain, but no. Well, okay, for you two, it'd be kind of like you set up a for loop, and you use like I or K or J or whatever, and that's local only to that loop. But you could, of course, use I or J or K or whatever in some other for loop. And if you nest them, you have to pick a different letter, but otherwise it doesn't matter. And what's the difference between I and J? Well, nothing, right? It's just what letter you picked. So yeah, it's sort of not letter dependent in that case. So yeah, anyway, okay. So now that said, we tend to pick t's and x's and things of those sorts because you know, we're thinking of these things as variables, and we sort of have a convention about which letters of the alphabet we pick to represent different kinds of ideas, right? T, X, Y, Z, those are going to be variables. A, B, C, right? Those are numbers. Yeah, and I guess that's the other thing I should point out here, that the bottom bound here is an A. A is some number, okay? Now, in the examples that we were cooking up last time, I just chose A equals 0 for simplicity. But it didn't have to be 0. It could have been any other number, okay? All right, so is that cool? Okay, so the wrinkle, oops. Will be what about if instead of an x up there at the top, we have something that has x's in it, but is more complicated? So I've called this u of x to mean some function of x, whatever it is. Okay, so for example, we could have like x squared up there or something. And so the question is, well, then what do we have to deal with? Okay? All right, so is that kind of okay? Yeah? All right, so what I'd like to do kind of next is sort of motivate maybe a little bit more in a different way than we did last time, the part B. Okay? And so for that, I think, let's do this with GeoGebra, actually. No, let's do it with Mathematica. All right, so let me pop open Mathematica and switch the source on. Oops, let me get a Mathematica Mathematica window actually open. New document. And okay. All right, so we're going to kind of do sort of like we did last time, but I'll do some graphs with it too. All right, so in order to do this, I need a particular function of f of t, right? I've got to pick something in order to compute and graph. So let's pick something, dang it, it would help if I could type today. Let's just pick t, okay? This is one that we did last time. And what was the antiderivative of this? Antiderivative. Right, okay. I might start threatening that, like, you can lose a standard, right? Right. Right, precisely. It's sort of the math equivalent of the Fifth Amendment, right? Yeah, you know, I will not answer on the grounds that this might incriminate myself. Yeah. Have any of you guys ever used that when you got in trouble? I did in 5th grade once. The teacher was not happy. Yeah. Yeah, I had this sort of feud with my library teacher in 4th and 5th grade because she was very much a, you know, that's a 5th grade book. You're a 4th grader. You can't read a 5th grade book. And I'm like, I want to read the book, dang it. And yeah, so that we had all kinds of fights. Anyway, I said something nasty about her, and she's like, what did you say? And then at that point, I invoked my Fifth Amendment rights and got promptly marched to the principal's office. That was good times, good times. All right, so I'll pick f of t as t. And if I graph this, I'll just plot it from 0 to 4. That's probably good enough. And not shockingly, what do we get? Straight line. Okay, great. All right, so what we did last time was we said, okay, let's pick a value of x. And if I start at 0 and I pick a value of x like 1, then the integral from 0 to 1 represents the area between 0 and 1 that's underneath the curve, okay, which is a triangle, right? And because we're not idiots, what was that area? Here, if x is 1. 1/2, okay, because we'd have base 1 here, height 1 there. The scale's a little bit off, so just keep that in mind. Base 1, height 1, area 1/2. Okay, great. So that would mean that this integral value, or this function's value at 1 was 1/2. And then we said, okay, well, what about if we plug in 2 and we got base 2, height 2, area 2, and so on. Okay, so we got various other values. Yes? Okay, so what I'm going to do here is I'm going to define a new function, and I'm going to use capital F here, right, because I'm thinking of it as the integral. And then let me go over here to palettes so I can do this with some symbols rather than just code. Okay, what were we defining here? Oops. Okay, so here's what I've got, right? I'm going to pick my bottom point at 0. We'll just start everything at 0. That's fine, right? And I'm going to go up to some mystery point x, and I'm asking what's the area from 0 to x underneath this function t, okay? So we have verified numerically, because we computed this last time, what is big F of 1? 1/2, right? How did we figure that out last time? Just with the geometry of it, right? And big F of 2, we said was 2. Big F of 3 was 9/2. Big F of 4 was 8, and so on. Okay? So we computed a few of those things just using basic geometry. Good? All right, so what I've defined here, though, with Mathematica is that thing as a function. Okay? So what this means is, like last time we only computed f of 1, 2, 3, 4, but could I do like f of pi now? Sure, and it'll compute it. Okay, no big deal. Okay, so what I want to do then is let me plot the big function. Okay, along the same range, 0 to 4, just for giggles. Okay, and so what function do we get here? Well, what does that look like, just picture-wise to you? What kind of function do you think it is? Or what kind of graph? Yeah, sure. Excuse me. Sure looks like a parabola to me. Okay. In fact, it is. But it's some interesting curve. Okay. All right. So let me choose a point on here. And for sake of demonstration, let me just pick this point there at 2, 2. Okay? That's a function, a curve, right? Could I ask what is the tangent line at that point? Yeah? Wouldn't that be fine? Okay, so what do I need to know to construct the equation of a tangent line? I need to know what two numbers. I need to know a point, which is really two numbers itself, and I need to know a slope. Okay, what gives me the slope? The derivative. Okay, right, which we'll get there, right? So I need to know the slope, which will come from the derivative of big F. Okay, and I need to know the point. Well, what's the point here that I've chosen? 2, 2. Okay, so I already know the point. That's easy. Question is the derivative. Okay, so the equation of the tangent line would be this. Y minus the y coordinate equals slope times x minus the x coordinate. Okay, then I have to say what range to plot it on. Now, I'm not finished yet because I just put m in there for the slope, right? Just to be lazy for right this instant. But I'm going to replace m with something. Okay? What gave us the slope? What tells us the slope? The derivative of something. Which function? Little f or big F? It's kind of a trick question. It's big F because what function did I plot there? What's this parabolic looking thing? Is that big F's graph or little f's graph? It's big F's graph. Okay. So I need to compute big F's derivative and then plug in a particular x coordinate. And what x coordinate am I interested in here? 2. So what I need to replace this with is f prime of 2. Okay, because that's the particular point that I'm at. Okay, we good with that? And in fact, let me do this. Since we're using Mathematica. Let's be smart. And this way you guys can look at whichever screen you wish. Okay, good? So let's run this and see what we get. Oh, sorry, forgot the double equal. There we go. Okay, well, great. That looks like a line to me. Right? All right, now, for my next trick, let's, this is a line that's supposed to be tangent to this curve, correct? So let me put them actually on the same graph, okay? So let me just do that real quick. using my wizardly mathematical powers. And then I'll do, there we go. Looks pretty tangent to me. Okay. All right, that's good. All right, now in this case, we've got that red line. Could you guys figure out, just by kind of looking at the graph, what's the slope of it? Okay, and notice that the x and the y scales are different, so you can't just eyeball this one. You have to actually do the rise over run thing. Slope is 2. Okay? We buy that? Yeah? All right, now, here's what I want to look at. What's the x coordinate that we're interested in? 2 was the one that I picked, just kind of at random. All right, if I go back up to my original graph, what is the value of that function at t equals 2? 2. It's the same thing we got the other way. All right, let's do this for a different point and make sure that I'm not, like, lying to you guys. Okay, so what do I have to change here to do this for a different point? Yeah, the f prime, so let's pick a different point. How about 3, just because it's already on our range. Okay, I need to do that. But then what else do I need to change? The point, right? Okay, so if I'm over here at 3, what's the value of the function at 3? It's actually like 4.5. Okay, so let's be smart about this. And let's put here f of 3. Okay, now last time with the geometry, we figured out that f of 3 was 4.5, right? But let's say we had forgotten that fact. So I'll just tell it to do the computation with that command. Okay, so if I run this, all that should happen, the blue curve will stay the same, right? It's the same parabola. The red curve, though, or line, will be a tangent at this point here, 3 comma whatever. So the tangent will just change because I've chosen a different point. Okay? Good. All right. Figure out that slope, please. Okay, so you definitely know 1 point, 3 comma 9/2. And then what's the other obvious point on here? Bueller. Yeah, 1.5 on the x-axis, comma 0, because it's an intercept. Okay, so now you got 2 points. Can we do some risey and runny stuff? And what, pray tell, do you get for the slope? Don, this is where the writing implement and the hand find their way together. Okay, so what do we get? What'd you get, Don?
I don't think it's 3 over 2.5.
All right, well, let's just double check. So if this point is at 3 comma 4.5 and 1 comma 0, then the slope would be 4.5 minus 0 divided by 3 minus 1.5. okay? Right, because it's 4.5 over 1.5, which is 3. Okay, good? Yeah? 3. Huh, that's interesting. Because guess what that is? Exactly the height of the function here at 3. Kind of cool? Maybe? Okay, so what I'm actually showing you guys is sort of the way that this part of the fundamental theorem was both conceived of and then proved by Isaac Barrow. Now, you guys probably never heard of Isaac Barrow before. On off chance, has anybody? No? I haven't mentioned it before. Well, you've certainly heard about the guy that came right after Isaac Barrow, who succeeded him as the Lucasian professor of mathematics at Cambridge. Any guesses on who that was? Newton. I think you've all heard of that dude. Yeah, so Barrow was one of Newton's teachers. Yeah, so he was the Lucasian professor before Newton was. Yeah. Fun fact, a future Lucasian professor is Data from the Star Trek. Yeah, in one of the episodes, he's the professor there. Yeah, it's kind of cool. All right, anyway. So now, this worked out maybe a little too easy because what function did I pick here to start with? T. Not all that interesting, right? But it did mean that we could work all this stuff out by hand. Okay, let me change this, and then let's redo everything else, okay, to see what's going on. All right, so if we did 1 and then we did t, what would be a good next choice? How about t squared? Good, right? All right, and again, I'll plot that from 0 to 4, right? So now our original curve is a parabola, okay? And could we, by hand, figure out some of these areas? Okay, how would we, by hand, figure out some of these areas?
Oh, you mean not doing any math?
Well, just because it's by hand doesn't mean you're not doing math. Right? What do you think people have been doing until about 50 years ago? Right? Or more like, I guess, 70 years ago now. Because in 1950, how many computers do you think there were in the world?
Maybe 1,
Like 5, right? Basically, almost 0. Yeah. And now how many are there in the world? Billions, right? Yeah, and you know, your iPhone has more computational power than every computer that was in any way involved in the entirety of the Apollo program. Kind of freaky, right? Yeah. Okay, so t squared. But, so how could I find areas underneath this curve without counting squares on like a piece of graph paper or something? Yeah.
the equation and find the antiderivative.
Okay, we could do that. Yeah, okay. So that's certainly one tool that we have at our disposal, right, is that we could just do it with the fundamental theorem. The other is because it's parabola, we could use that trick from Archimedes that I showed you guys last time. If we're a little clever with how we set that up, we can use it, okay? All right, but we'll just let the computer do it for us for now. So I'm going to redo all of this stuff, okay? And in this case, because I defined my function, oh, this one, sorry, I need to do, I'm going to do f of t there, which was t squared, okay? That, okay? Now, the graph here, actually, let me switch the order here. Maybe that'll do better. Oh, I know what the problem is. Here, there, that's better. Just basically had to graph more of it. Same line, just I just extended the viewing window a little bit. Okay, so the blue curve is the this antiderivative, right? So it's sort of the accumulated area. And what does that shape kind of look like? I mean, you might say it's sort of a parabola. It's not a parabola, okay? But, all right, it's some curve. Let's just suspend disbelief as to what it actually is for the moment. But at the point 3, I've drawn the tangent line there, okay? And what is the value of this function at 3? Well, it's a little harder to read off from the graph. Okay, I mean, it looks like it's pretty close to 10, but is it exactly 10? Well, I don't know, right? So what are we really interested in, though? What about that red line am I kind of curious about? I'm curious to know what its slope is, right? That's what I had you guys computing a minute ago with rise over run business. So what is the slope of that thing? Well, it's whatever f prime of 3 was. In this case, it just so happens to be 9. Does that look reasonable looking at the graph? Yeah, seem plausible? Okay. All right. So at 3, what was the slope? 9. Okay, we good with that? At 3, what is the value of that function? The slope of one function is the value of the other. That's the geometric interpretation of the fundamental theorem, or this part of the fundamental theorem. Okay, does that kind of make sense? Yeah, so here's Isaac Barrow. I spared you guys the Latin version. Yeah. All right. Question, preguntas, fragen. Value of the other, right? So the slope of the integraled version is the value of the non-integraled version. Okay? Good? The area underneath this guy from 0 to 3. Okay, I think in this case, yes, by coincidence. Yeah, because if we compute, for example, f of 3, yeah, okay, it's coincidence that they're the same number in this example. Okay. Yeah. Because, like, for example, let's say that I change this to t cubed, okay, and then I redo this. The value of the area is 81/4, but the slope is 27, okay? So the fact that they were both 9 there was just coincidence, okay? All right, is that okay? Yeah? All right, so that's the sort of interpretation of the fundamental theorem. All right, so let me go back to the iPad. And here. Okay, and let's talk about the one wrinkle that we haven't yet, which is this. Okay? So what about if the thing at the top of the integral was not just x, but rather some function of x? Okay? So here's kind of my thought process. Let's call this thing f of u of, well, yeah, let's call it f of u of x, right? Because it's fatty f, but there's some function plugged in at the top, right? And I'm asking, what's the derivative of fatty f of u of x? Well, what is the derivative, like what rule do we need to use here? The chain rule. So what's the derivative of f of u of x? F prime of u of x times u prime of x. Okay? So are we cool? That's the chain rule. Okay, yes? No, we're not finished yet, but is that step okay? Oui? Ou non? Okay, so we got that. Now, u prime of x, this guy, well, if we knew u, could we compute u prime? Yeah, if like we had the formula for u of x, then using the different rules and stuff that we know, we could figure out what u prime is. So it's okay for me to just, in this instance, just write u prime. That's it. Okay? But can we do a little bit better with rewriting this? Little bit, okay? Because what is f prime of u of x? What does that mean? This means take the derivative of f of x, then plug in u of x for x. Okay? So what is this? Well, this is really asking well, how is big F defined? It was defined as an integral, right? Well, what's the derivative of an integral from a to x? Now what are we applying? Right, so what is this? F of, careful. Okay, that's f of x by the FTOC. And then what do we still have to do? Because I still said I have to plug in u of x. All right, and so what I would get is f of u of x. Okay, does that make sense? So it's the inside function with u plugged in for x. Okay? All right, so let's put all this together. So d dx of a to u of x of f of t dt is f of u of x times u prime of x. Okay, and this is the wrinkle version. Okay, it's essentially just the chain rule, right? Thou shalt obey the chain rule. Okay, so let's work an example of this. And let me give you guys a minute to make sure you've got everything down and you're ready to, because I'm going to have to move to a new sheet of paper. Okay, so just let me know when we're good to move on. Hand on your head when you're ready. Okay. Actually, you know what I need to do, Owen? Is I need to get a bunch of like Arduino Nanos with 3 buttons, or maybe several more buttons with LEDs. And then instead of the cups, you could just have like little battery-powered light thingies. Wouldn't that be kind of Gucci? Yeah? I'll get right on that this summer. Yeah, that actually would be pretty easy to do, too. Huh? In fact, I wouldn't even need an Arduino, right? If there's buttons, just need some transistors and maybe a couple of SR latches or something. I don't know. Okay, so ready for the next sheet? We good? Yeah? All right, so what I want to do is do sort of a specific example of this with actual functions, like actual formulas. All right, so let's pick, how about this? Let's start with this a little bit neater. Okay? d dx of a to x of e to the minus t squared dt. What's wrong? Okay. When you look at that, like, okay, how many of your moms or dads, like my mom in particular, is like, if I wrote that down and put it in front of her, she'd be like, what is this, like, you know, do I need to call a priest to have you exorcised, kind of thing, right? It looks frighteningly scary, right? There's all these symbols all over the place, okay? What does it mean, right? How do we decode this as a human? Well, what does this part mean? It's an area between a and x underneath this function, and I just picked for funsies e to the minus t squared. Okay? So that's some sort of area thing, and it's going to be an answer in terms of x. So it's a function in terms of x. Well, if it's a function in terms of x, can't I take its derivative with respect to x? Sure-see. Okay? And as scary as that looks, the fundamental theorem is what saves the day, because what does it say that this is equal to? Huh? Yeah, or in this case, right, e to the minus x squared. What did I do? I plugged x in everywhere I saw t on the dude on the inside, and that literally is it. Okay? Does that seem too easy? Or too good to be true? Okay, right? If there's anything you guys should have learned in your 18 or so years on this planet, it's that if it's too good to be true, it probably is. But this is one of those instances where it is not, or right, it is just that way, right? Okay, but it's only this easy because we know the fundamental theorem. Otherwise, we'd be hosed here, like completely. Okay? All right, so let's do a spicier version of this. Let's work our way up to some mango hob. Okay, now what? What does the fundamental theorem tell me to do? What am I going to do with the sine x and the e to the t squared? I'm just going to plug it in. But then what do I have to multiply by? To multiply by that by the chain rule. Okay, so what did I do? The thing I was integrating, I just plugged sine x in place of t. That's it. But I have to multiply by its derivative by the chain rule. Okay? Now, what's the derivative of sine? Cosine. And that's literally it. Okay. Now, I love this. This is a good example of a problem because what was the other version of the fundamental theorem? Yeah, go ahead. Sorry, Cindy. No, just, yeah, okay, good question, right? What I'm taking the derivative of is the thing I plugged in, which was sine x, not the whole top part. Yeah, you're right. Like, up until now, we've had to worry about taking the derivative of the entire exponent, okay? And that would still be true in normal circumstances, but this, we don't have to do that, okay? Yeah, do you guys see what Cindy's question is? right? Notice that the chain rule told me to take the derivative of sine, not minus sine squared x. Okay, okay, good. Okay, so what was the other version of the fundamental theorem? It was about antiderivatives, right? So we could have done this problem if we knew, oops. This represents an antiderivative of e to the minus t squared, right? And if we knew such an antiderivative, we could have used the other version of the fundamental theorem. All right, here's the problem. Do we know what the antiderivative of e to the t would be? Yeah, e to the t itself, okay? E to the t squared, or e to the minus t squared for that matter. This is really disturbing. We don't know the answer to this. In fact, we know there isn't one. Okay, so it is impossible to find that antiderivative. Okay, this is why a function like this is sort of golden for calculus teachers who want to really make sure their students understand one part of the fundamental theorem by making it so that you can't use the other. Okay, so let me just kind of elaborate. What do I mean by this is an impossible question? Okay, so okay, so there's a big pile of functions that we call elementary. Okay, and pretty much every function you've ever encountered in your life we consider to be elementary. So what are they? All polynomials, square roots, trig functions, e to the x, the logarithm. Am I missing anything? Fraction stuff. Okay, so it's anything that you can build out of these basic pieces, which, like I said, would be polynomials, radicals, logarithms, trig functions, e to the x, all of those guys. And then how are you allowed to combine them? You're allowed to combine them with addition, subtraction, multiplication, division, and the fun one, composition, right? So you could say, all right, a polynomial is elementary. This other polynomial is elementary. If I put one polynomial on top of the other polynomial and I've got this big horrible fraction, that new function is still elementary. Okay? So, if you take the derivative of an elementary function, you get another elementary function. Now, why is that true? Well, think about what the derivative rules are, right? You know the product chain quotient rule, and those are really the only ones, well, and the sum and differences and stuff. And if you know all of those, and you have enough paper, and you don't screw things up, it might take you 1,000,000 years, but could you compute the derivative of any function? Just take a while, possibly. But when you do that, you never leave the group of elementary functions. Okay? Doing this with antiderivatives is not true. Okay? So if you do antidifferentiation, sometimes the antiderivative, you wind back up in the elementary territory, but not always. Okay? And when the not always happens, we call the resulting thing, whatever it is, it's not elementary, so we call it special. Okay? So the integral of e to the minus x squared is an example of a special function. Its antiderivative, or the antiderivative of e to the minus x squared, cannot be expressed in terms of elementary functions. It's somehow outside that universe. Okay, is that okay? Yeah? All right, so, right. Now, what we're going to start talking about on Friday is the art of finding antiderivatives. Okay, what I've said here is that it actually is impossible in some instances. And that's unfortunate, but them's the breaks. But there's plenty of ones left over that we can still figure out, even though they're not going to be easy. Okay, so the art of doing that is Friday's topic. Okay? All right, now after class, Canvas is horribly broken. I've got all kinds of things to fix with it in terms of assignments and stuff. So don't freak out when you get like 10 notifications that new assignments are there. Okay? Because you're about to get like a bajillion notifications. So just don't freak out. Oh, and the other piece of business is, what were we supposed to do on Monday? Yeah, we're not going to do it Monday. We're going to push it back to Friday next week, okay? Just so we have a little bit more time to finish this antiderivative stuff, and so you guys will be good to go, okay? And for those of you who have scheduled an appointment already for this week but haven't let me know which ones you want to do, please just send me a quick note. And for those of you who have already scheduled and done it and stuff, yay, okay? All right, see ya. And Mr. Fisher, I hope you're feeling better.